Welcome. I'm Robert Kilpatrick. I'm the chair of the Health and Medicine Member-Led Forum and the host of the Healthy Society series here at the Commonwealth Club. I'd like to welcome everyone in this audience tonight to the Commonwealth Club and also online. We have an online following, so welcome. Please silence your phones. The last time I said that, my phone went off by mistake. Also, there are question cards on your seat, and there's some pencils. So the way it's going to work is that my colleague, Billy Bean, who's standing back there in his beautiful blue outfit, who happens to be head of membership at the Commonwealth Club as well. If you have any questions, he's going to be collecting question cards and handing them to me. And of course, I'm going to screen out all the really good ones and claim that they're mine. Not really. I'm going to say a few things about the Commonwealth Club and about this series, then I'll introduce our august speaker today. Commonwealth Club was founded in 1903, long time ago. And recently we merged with the World Affairs Forum, so now we're called the Commonwealth Club World Affairs. So we're now way beyond the Bay Area in the United States. We're a global entity. We have followers all over the world. This is the oldest and largest public affairs forum in the nation. And given what's going on in the country now, we're very pleased to be a kind of bastion of free speech across chasms and differences. So thank you for coming. One of the best things I ever did in my adult life was to join the Commonwealth Club as a member. It's a phenomenal experience. It gives you, by the way, there's a special offer now, I've been told. $99 a year, which is quite inexpensive, regularly $139. So when I joined the Commonwealth Club many years ago, I started learning about things that I didn't really know about and I didn't think were that important. And all of a sudden, I joined the Member-Led Forum for Health and Medicine. And then before you know it, I was the chair of it. So we have member-led forums on about 25 different areas of the economy. And if you're a member, you can join one, you can help shape topics, you can meet interesting folks like Tim Chow. So I encourage you, if you're not yet a member, for a very trivial sum, do so. You get special discounts, access to special events. Sometimes we have wonderful parties on the roof with a view of the entire bay. It's not so obvious if you just sit at home and watch programs online what you're missing. So if you want a strong social life and you want to meet new people, this is a good place to do that. Today's program is part of the Healthy Society series, which I have hosted since the start of COVID. So for the first time since we were founded in 1903 with a fabulous media team, we went 100% online because the city of San Francisco closed the doors to this building. So for 3 years, the Healthy Society series project was aimed at looking at how individuals, families, communities, the nation can be healthier, but also the body politic. And this was before some of the big political changes in the United States. What does a healthy society actually look like? And I don't just mean diet and exercise, so democracy, this kind of thing. So this program is part of that. A major topic is artificial intelligence, or AI as it's commonly known. And this word evokes strong emotions in many people. Hope, fear, uncertainty, and curiosity. Certainly, I'm curious. So in the spirit of all of this, I'm pleased and honored to introduce our speaker today, Tim Chow, founder of the Pediatric Moonshot, and he's already given me the lapel pin. Someone said it looks like it might have a microphone in there, and it's a spyware or whatever. I'm not so sure about that. But it looks very nice on my jacket. For those of you who don't know him, although some of you do, he retired from the Oracle Corporation as the first president of the cloud computing business, and he returned to Stanford University in 2005 with the first class on cloud computing. So Tim has a very strong positive vision of AI in healthcare, and the Pediatric Moonshot project he leads addresses 3 major unmet needs: reducing health inequity, lowering costs, and improving outcomes for children. And in the United States, many people know that healthcare for children is often seriously ignored compared to healthcare for the elderly. So there are question cards. Please feel free to fill them out. They'll be collected by Billy. And if you're attending online, some of you are, you can leave questions on the right-hand side of your screen, and we'll be picking those up and asking them. So without further ado, Tim, I know you've got an exciting presentation, and then you and I'll have some discussion, and then we'll have some questions from you and online, and we're off to the races. Welcome.
Well, thank you for that great introduction. What let me do today is really kind of take you through our journey of what we call the Pediatric Moonshot. I want to talk about 5 big things. One, kind of give you guys a glimpse of what pediatric healthcare looks like, predominantly in the U.S., but outside the U.S. as well. Talk about how AI could make a difference in all of this, why the current mechanisms will never work, and why we developed a totally new approach, something we're calling distributed AI cloud infrastructure, and finally give you some ideas of what kind of applications could be in front of us as we go into the future. And the part I'm going to end with is we're actually using this event to kick off a capital campaign of $50 million, and so I'll talk a little bit about what we're doing over there. So with that start, I'm going to talk about hopefully long life for kids, but I'm going to start out with something probably even more important for everybody in the room, long life in your personal life. This is actually taken from a temple in Kyoto, Japan. It's believed to be over 500 years old. It contains the 10 secrets to long life. So everybody in the room is writing them down. Okay, so here's it translated. I'm sure everybody's doing this, eating more vegetables and less meat, having more sleep and less worry. And then the one I've always found personally amusing is the more bathing, less clothing. So, I guess if you're a Buddhist monk 500 years ago, there wasn't much in terms of entertainment. So there it is. So if you walk away from this with nothing else, maybe a few lessons for long life for you. I'm going to start the story in that classroom. So as Robert said, I started a class in cloud computing at Stanford. In fact, we just started it again this quarter. I think this is the 15th year. About 7 or 8 years ago, I have a strange student arrive who sends me a note and says, "I'd like to meet you." And I went, okay. So we met, for those of you who live in Palo Alto, we met at Joni's Cafe on California Avenue. And this guy walks in. I'm looking at him going, doesn't look like a regular student. He sits down. I discover he has an MD, an MPH, an MBA. He's chief of pediatric cardiology at the Children's Hospital of Orange County. And so I'm looking at him going like, why are you talking to me? I don't know anything about what you know about. But Anthony, his name is Anthony Chang. Anthony was in town because he had watched Jeopardy, and he was convinced that AI, big data, and cloud computing need to meet medicine. So like any regular person, he decides to enroll in the bioinformatics program, which is one of the top programs in the country. Later on, we talked to the department head, and they said, oh, yeah, we let him in because it was such a curious application. It takes him 3.5 years to finish a 2-year program because, number one, he has no idea how to code. Number two, he has a real job. He's head of pediatric cardiology. And number three, I think he's like 52, 53 years old. He decides to adopt an 18-month-old and a 6-month-old, and he's a bachelor. So I love telling Anthony's story because it's never too late for any of us if you have the will. And obviously, Anthony's a smart guy. Anyway, I had never spent any time in healthcare up until meeting Anthony. In fact, in a lot of ways, kind of stayed away from it from a commercial point of view. And so Anthony, I like to say, adopted me. And so what I'm going to share with you is some of the things I learned, which starts with, I have a slide up here. This is an ultrasound image. He was providing consulting for a little kid in Myanmar. The local team wanted to share an ultrasound image with him. They couldn't. At the end of it, the baby actually died on the operating room table. He later on got to see the ultrasound image, and he said, I could have told him what to do and saved her life. And that was the beginning of my introduction to kind of where they are in the current world. If you look at it, I told you a story about Myanmar, somewhere really far away, but this phenomena occurs right around the corner here. Howard Memorial is in Willits, California, which is just north of here by about 4 or 5 hours, population 5,000. There are no pediatric expertise, zero in that entire hospital. As a result, 20 times a month, they ship kids to UCSF, Stanford, Shriners Burn Unit, and UC Davis. Oftentimes on a helicopter, or they're navigating what the traffic is going to be like in San Francisco and then diverting. And by the way, with a CD-ROM in the helicopter. But it's great. I got the image. I'm going to tell you a story of a kid in Southern California. So he gets hit on the head. He gets taken into the emergency room at the local community hospital. They MRI image him. They go, nah, he doesn't have a concussion, and they sent him home. 6 to 8 weeks later, he's still having issues. They take him to one of the larger hospitals. They re-image him, by the way. They look, they go, nah, not a concussion. 6, 8 weeks later, he goes to a third hospital, is re-imaged again, and they go, yeah, he doesn't have a concussion, he has a brain tumor. So it's kind of curious, right? The human confirmation bias that obviously he got taken into an emergency room and was told he was hit on the head. Well, of course, you'd be looking for a concussion. But you can see that human after human. And by the way, they actually ended up being able to see the MRI image of him from the very first time. And they said, yeah, you could actually see the tumor there. There are unintended consequences of misdiagnosis. This is actually a story out of Texas. A kid had a broken bone, was taken into the local hospital, x-rayed, and the conclusion at that hospital was this was child abuse. So immediately they brought in law enforcement. They actually took the kid to Texas Children's. Texas Children's re-imaged him and looked at it, and they said, this is not child abuse. And you can imagine what that family went through, et cetera, right, in that situation. So those are kind of common things, right, fractures. But there are plenty of rare things that occur in the world. I'm going to tell you about one of them. This is a condition called focal cortical dysplasia. It is a brain lesion. For those who can see the slides, what you are looking at on the left side is an MRI image with that little arrow pointing to the brain lesion. And like me, you're probably looking at it going, well, how is that any different than anything else? The image on the right side actually is an ultrasound of the same lesion. Now, the implication of this issue, this lesion, is that the kid has epileptic seizures. There's a kid in Florida who is, I think, about 13 years old. For the past 12 years, he has had epileptic seizures 2 to 3 times a day. At night, he wakes up screaming. They MRI imaged him very early, didn't see anything. They started giving him drugs. Some they could afford, some they couldn't. They were getting ready to actually put in electrical implants into his brain. They re-MRI imaged him, and now they believe he has this condition, FCD, which, by the way, you can use surgery and take out that lesion, and the kid's cured for life. So good news. This only happens about 25,000 times a year in the U.S. Bad news. No one pediatric neuroradiologist sees enough of these cases to be able to recognize that this is focal cortical dysplasia. And it's not only things which can be, let's call it, therapies which are surgery that could correct it, but there are many rare diseases which can be controlled, solved, et cetera, with approved therapeutics. What you're seeing up on the screen here is 60 of them that we have identified where the pharma companies have developed drugs for all of these conditions. But when you look at these conditions, and we've spent a lot of time in rare kidney disease, you quickly realize how the heck does any clinician able to recognize that this is FSGS or any number of these things. In particular, FSGS, which is a kidney disease, I was talking accidentally to one of the world's experts in this, and I said, well, like, where does a clinician learn this? He goes, oh, yeah, there's a lecture on FSGS during med school. One. And if you happen to be paying attention on that day, maybe you know how to diagnose FSGS, but highly unlikely that that's true. So I'm going to end with some statistics, just get you guys thinking about this. In the U.S., 60% of the rural counties, remember I talked about Willits, California, 60% of the rural counties have no pediatric expertise whatsoever, right? We have about 3,000 pediatric cardiologists in the United States. I will tell you, most of them live in the major metros, right? Meaning San Francisco, LA, Boston, et cetera. They are not in Eastern Oregon. They're not in Idaho, Alaska, any of these places, okay? 3 states, you see them listed up there, have no pediatric emergency physicians that are trained in this. 0, like a whole state has nothing. If you leave the U.S., remember I said there's 3,000 pediatric cardiologists in the U.S., there's about 300 in India, and we all know the population of India. And if you go to Africa, in Rwanda, there's one guy who's a pediatric cardiologist. So you sit there and you go, okay, I mean, what? We're going to build more med schools and train more doctors and incent them to live in Eastern Oregon? I mean, is that how this all is going to work? And so all of this came together during the COVID time. I'm sitting around thinking, maybe rather than watch Netflix all day, let's go do something useful. So I grabbed a group of engineers and we gave ourselves a mission. And our mission is to reduce healthcare inequity, lower cost, improve outcomes for children locally, rurally, and globally. So how are we going to do that? By creating real-time, privacy-preserving AI applications based on access to data in all 1 million healthcare machines in all 500 children's hospitals in the world. That is what we call the Pediatric Moonshot, which I think we all can agree we named it correctly. So let me talk a little bit about, so that's the current world, why we think this is an important thing to go do, an important goal. Let me talk a little bit about where the world is today. So for those of you who've been being students of what's going on in the world of AI, one of the things that's happening, and we hear it all the time, is that there are large data centers being built in Texas. In fact, one of the very first data centers at Oracle was actually in Austin, Texas. So the current way that everybody thinks about building AI applications is you centralize all the data. You bring all the data into one location, giant data center in Abilene, Texas, or whatever, and you learn on that data. And that is the core of what we are today seeing as ChatGPT or Claude or any of these things, right? Our contention is that's never going to work in healthcare and life sciences. Number one, the data sizes are much larger. You may not be aware of this, but an ultrasound study is 1 terabyte. Like just one study is 1 terabyte. To give you a sense of scale of this, we actually did the back of the envelope. The 500 children's hospitals in the world generate 6 million terabytes of data a year. So these things, there's a huge amount of data. So, are you going to move all that data into one center where in Iceland or something? Number 2, what about security, right? I mean, this is personal information, healthcare data, et cetera. And then last, what about privacy? You may not be aware of this, but in Norway, as an example, they are saying Norwegian data is never leaving Norway, right? So we're saying, well, okay, centralized is never going to work because privacy, security, data sizes. So fundamentally, this is like computer science 101. We said, well, rather than move the data to the application, let's move the application to the data. So we engineered a distributed AI cloud infrastructure, which literally puts a server inside the building at a hospital, clinic, and by the way, an ambulance that now can get. So why do we need to put it in the building? Well, remember I said the objective was we wanted to build real-time systems. So the only way you can get real-time, I'll pick on ultrasounds for a minute. The only way you can get real-time data from an ultrasound is you have to be on the network in the building with the ultrasound. So we mastered the fine art and science of how you do that, because by the way, the very first time we talked to the IT guys, you can imagine it was followed by the three-letter acronym NFW. Yeah, they're having nothing of this, right? We go all the technical detail of how we were able to achieve this, but just to let you know, we actually deployed what we refer to as zones in 8 sites on 3 continents because we wanted to prove that we had built a global infrastructure. Okay, so a global infrastructure that now allows me real-time access to any data, ultrasounds, MRIs, EKGs, blood analysis data, et cetera. So what I want you to think about is that, in essence, what we're doing is not a whole lot different than what Apple did. So Apple created infrastructure called a phone, distributed around the world, gave programmers access to a camera and access to GPS information, and then told the world, go build, Uber and Lyft and Instagram and all of that. This is very much the same approach we're taking. This is, let's go free up the data in a privacy protected way. Okay, for a set of cardiology, oncology, orthopedic, et cetera applications. So what could those applications look like? Let's talk about that for a second. So remember I said, let's talk about our focal cortical dysplasia example, right? Well, I could build an application, if I had the data, to be able to detect focal cortical dysplasia if I had access to all the MRI images because, right, that's an easy way to train those things. We are actually tracking 140 research applications around the world where a team at Stanford or at UCSF or in Boston or in London, whatever, has gotten a group of ultrasound images, MRI, X-ray, built applications that can detect bone fractures, can detect pancreatic cancer, et cetera. What you will see across the board in all of those is they're trained on very small data sets, right? Like 100 images, 1,000 images. In fact, a paper was recently released by 2 guys at Stanford and at MIT that basically looked at all of even the FDA approved, quote, imaging applications. And what they saw is that, they work on the test data set, but as soon as they move into the wild, they don't work very well. Well, this is fairly obvious why it doesn't work very well, right? We're sitting in San Francisco, right? If you took a Waymo car here, trained on all the data about San Francisco, and took it and moved it to London, do you think it'd work very well? No, not at all, right? And so the fact that these have been trained on very small data sets, it's great for a Nature magazine article, which is what they usually end up being, but it doesn't really impact anything on the clinical side, which leads to the really innovative. So we can say, I can take an application, what is called inferencing, for brain bleed, for FCD, for bone fracture, and I can run it at the point of care in real time. So now our brain tumor example with MRI, you could have a brain tumor detection algorithm that's sitting there running in real time on every MRI machine in the world, right, detecting brain tumors. That's cool, but how is that going to be accurate, right? So the key question becomes, well, how do you train on this data when you're not bringing it into one location? How do you train in a distributed world? And so we took a lesson out of our friends on the consumer side. You may not be aware of this, but if you're holding an iPhone, Siri's trying to get smarter about listening to you, about understanding what you're saying. How is it doing that? is it taking your voice and sending it to the Apple Cloud? Well, no. I mean, what about privacy? And who's going to pay for the network bandwidth for that? So instead, what they pioneered is what has been called federated or distributed learning, which is let me learn on that local device. Let me learn on that phone. Let me learn on 1 million phones. And I'm going to take what I've learned from all 1 million phones, aggregate that knowledge, which is a bunch of floating point numbers, and then build a new generation of Siri, which I will deploy back onto those phones. We've done preliminary work that says this can work with medical imaging, medical data. There's actually 2 teams in Germany that we've been working with that have also proven this out, that this is possible to go do. Which leads us to where we're headed. So we are headed to building a distributed AI lab for children's medicine, 32 sites, all imaging machine data available in real time. All PACS. PACS is an application which the radiologist uses to annotate images. All PACS data available, and then all the EMR, electronic medical record data available, 2 authorized applications to, I'll say, perfect the art and science of how you build distributed learning with medical imaging, with medical data, et cetera. We're estimating this at roughly 3,000 servers deployed, roughly 2,000 terabytes of data flowing through this on an annualized basis. We've projected this at rough 50 million. I've been funding all of our efforts to date. That number is a little bit beyond my capability, which is why we have just constituted Pediatric Moonshot as a 501c3 and have a target list of 102 private foundations, community foundations, corporate foundations who have historically donated and supported children's medicine across the United States. Actually, there's a huge one sitting in the UK. And so we're starting that process with them to basically complete this distributed AI lab for children's medicine. I'll just end there, and we can ask questions, right?
Well, you and I'll have a little conversation, and then we can invite questions from the audience.
Well, go for it.
Okay.
It'll be more fun.
I noticed that the timer is not working.
I thought they were giving us extra time.
I thought to myself, the time is standing still. You have frozen the timer.
I've frozen time.
But I have a wristwatch, so I'm keeping an eye on it. There's an awful lot here, and it's unbelievably exciting. Looking to the future, building a distributed AI lab for children's medicine. And I thought to myself, surely this is scalable to every aspect of healthcare, every disease that exists in the world.
Amen.
So what you're doing now is the first page of a very long book. Is that true?
Oh, yeah. In fact, I just got off a call this morning. We just explain a little bit of structure. We've set Pediatric Moonshot up as a 501c3.
Yep. Mm-hmm.
There is a corporation called Bevel Cloud, conventional corporate, for-profit corporation, which owns all the intellectual property of the infrastructure piece of this.
Okay.
We just started a conversation with, I happen to know the CEO of the National MS Society. And we've been talking a long time about, let's go build a distributed AI lab for MS.
Okay.
Yeah, very same idea, except we're talking about 32 sites which are deep into MS. We're talking about a series of applications which are all about early detection of MS. And so they are going to start a campaign to raise the money to build a distributed AI lab to use. In fact, we were talking about the phrasing that AI could end MS.
Wow.
So yes, this is hugely replicatable across other diseases. Obviously, our computers have no idea if they're in a children's hospital or an adult hospital. So yeah, but the organizing principle of everything we did was the moonshot.
So the starting point for this was when Anthony came to you, right? And that's how you ended up with the children instead of something else?
Yeah, I think what happened was Anthony's a major league networker.
Okay.
He used to host a conference called what was it called? PEDS 2040. It was trying to project what pediatrics would be in 2040.
Okay.
So he invited me to come down and do a talk there in beautiful Laguna Niguel.
Okay.
So I said, okay, yeah, it's good. We go down there, and I told you there's 500 children's hospitals in the world.
Yeah.
I'm pretty convinced 200 of them were in the room.
Okay.
And it wasn't like an administrator or something. It's the gastroenterologist who wants to talk to you about graph databases, a very interesting breed. So I think because Anthony had already, in essence, his community was already cultivated as people who were on this bleeding edge, number one. Number two, children's hospitals, by definition, know they have to work together. No one site, Stanford, Rady's, Lurie's, Boston Children's, they all know that any one of them don't have enough data.
Right.
So how do they cooperate became much easier to think about than showing up at Intermountain or Kaiser, who would argue, oh, we have a lot of data, which is fine. I'm glad that they do. But I think because of Anthony, because of those people, and once you hear these stories, you're going, we have the technology to go do this. I mean, why don't we do this?
So thinking of the bigger picture, basically embracing all of health and medicine, is this kind of a use case? Is this a discrete project, and you could say, we have now demonstrated the use, the technical capability, and now we're poised, once you've achieved these goals, to move on to other areas of healthcare?
I think it'll be, as this continues to mature, I think we'll call it the marketplace, the world will tell us what's to do next.
Right.
I think our focus right now is the Moonshot mission is why I came out of retirement to do this. I didn't come out of retirement to go build a company, really. I came out to go do this project and get this done because we can.
And not to watch Netflix all day.
And not to watch Netflix all day. So, yes, we all know that this could be applied way beyond pediatric medicine, but no, we want to get this part done.
So the story is very positive. I'm sure everyone would agree this is okay, so let's play the devil's advocate for just a moment. Okay? 500 children's hospitals. Who's going to say to you, no way? You had alluded to a situation in Scandinavia or whatever. We don't allow the data to leave. Where's the pushback, and where are the obstacles for this vision to convert to reality?
You have a big sheet of paper?
I do.
I can list all of them.
I do. Why don't you list a few?
I made mention that I think this is, let's just talk about how startups work in general.
Yes.
So startups never work by, you go to customers who ask you, who else has installed this? What's the ROI? You have to find people who are visionary, who believe in, they buy the vision more than they buy the product.
Yeah.
So there are countless conversations we've had which end up with, well, when you get 3 applications running on 10 sites, we'll talk. Fine, right? So I think what ended up happening is we ended up in all the different places where you have early adopter mentality. And that could be, by the way, Nemours Children's in Delaware. My very first conversation was the CEO of the hospital.
Okay.
Right? Now talk about objections. I got out of that meeting, he goes, we should do this. So I said, cool, man, right? Let's go do it. From the time he said, let's do it, till we actually put a server in the building, you want to guess how long that was?
In front of a live audience? 18 months.
Oh, well, actually, I feel good now.
Yeah.
It was only 12.
Oh. Okay.
And I think, I'm chairman of an accelerator, B2B accelerator. When the kids come in and want to work in healthcare, I look at them and I go, you sure? Because the length of time this stuff takes is crazy. I mean, we go through security reviews, privacy lawyer attorneys, right? We just did work in a big hospital in the Midwest. I think there were probably 6 meetings where we had 5 network engineers in there because they didn't actually understand how their whole network worked. Okay. And we have a very prescriptive way in which this goes in. So it just elongates time. But I think at this stage, in fact, In our proposal document that we are sending to the foundations, we have 80 signatures of leading CEOs of hospitals, heads of cardiology departments, right, et cetera, who all they believe in this vision. They believe this is really where we ought to go. So I'm not saying we've hit critical mass. I don't know where that is. But we're way beyond just, it's an interesting idea that Tim and a bunch of guys in Silicon Valley thought of, to having a very large constituency. In fact, I have up here this screenshot of pediatricmoonshot.org. Take a look at the people section when you get a chance. There are probably 20 different podcasts there representing people in AI, in medicine as futurists, CEOs of major hospitals, leading AI researchers in medicine, who are all on there basically being supportive of, let's go do this. So, yeah.
I did my homework. I did look at that, and I was extremely impressed. That's partly why I wanted you to come here today. So I'm an advisor to the health and bio group at Berkeley Skydeck, which is the leading accelerator and incubator in the United States. And so I'm well aware of how long and how much money it takes to launch anything, and also the high rate of failure, which of course you know about. You're way beyond the beginning. So one of the questions I have is, you mentioned this program could be part of a kickoff for a fundraiser, $50 million. What are you going to do with the money? How do you arrive at that number?
I can show you the spreadsheet. So it is a combination of things. So it's capital.
Yes.
But it's also, remember what I made the point about. This is 3,000 servers operating in 32 sites.
Yes.
That is not going to be done with human labor.
No.
Right?
Yeah.
So we are investing a lot in automation so that these servers, these applications the security, the performance, the availability, the change can be managed with computers at scale.
What are you building versus what are you buying?
Yeah, so we're not a hardware company, so we are going to buy hardware, right? We've called it a big block mentality. So we're leveraging lots of pieces of software and services that other people have built and built on top of them, which is I'll say that's the way to do it today. But it's really all focused on, let's go deliver high quality compute, storage, networking, data services, distributed learning services, right? Which today there are a number. In fact, there's a group that was just here called Flower. There's a number. NVIDIA's doing work in this area that have built what are called federated learning stacks. We're going to go out with supporting many of those in a cloud-based environment, and then I think rapidly evolve to. I'll just give you an example of something we're already working on. So I made mention that we have the capability to talk to the EMR, right?
Yep.
So we're in the middle of building, in essence, patient digital twins.
Okay.
Right? So I can take your medical record, right? And now I can, for those technical people in the room, I can train on that. And now I can ask questions about your medical record.
Right.
Right? Mm-hmm. We did this with a bunch of oncology patients.
Okay.
The first thing we had no clue about was how big these things are. So an oncology patient medical record can be 3,500 to 7,000 pages of PDF, which is why once you see that, you realize when you go in the doctor's office, we always experience this. They ask you all these questions, and you're looking at them going, wait, you have all of that data. Once you realize they're actually looking at a PDF document with a search bar, you realize it's easier to ask you than ask the PDF document. We've transformed that completely so that now it looks a lot like a chat interface. We shared it with 12 oncology nurses around the country. Totally surprised, because we have no idea why anybody uses a medical record. One of the oncology nurses said, in chemotherapy, one of the things I have to do for the patient every time is calculate the total amount of cisplatin that the patient's been given.
Wow.
And were there any adverse reactions?
Yeah.
She says, it takes me 15 to 20 minutes to do that every time.
Yeah.
So we demonstrated this where, I mean, it's super simple. How much cisplatin was the patient given? Boom, right?
Yeah.
And so we're taking that as the basis of we're calling it a patient digital twin, which now, by the way, could be added in with wearable data and other data about you.
Sure.
And now, which is, I showed you that whole thing about rare diseases.
Yeah.
And asked the question, well, how the hell would you know you had FSGS? So we have already built AI agents for 3 rare kidney diseases, including FSGS. It's a fairly simple idea, which is we just allow the agent to ask a series of questions. Some of them are simple, like what's the height or whatever. Some of them are, well, was the urinalysis result over 3 or the blood analysis, et cetera. On a positive answer to any of those questions, a certain confidence level is applied to that answer. The agent runs, it sums it all together. It's under 50, it goes, nothing. It's over 95. Oh, plop in the medical record. It is highly likely this patient has FSGS. Let me show you the 34 reasons why we believe that to be true. And oh, by the way, here are the 3 approved therapeutics along with all the point of care information you would want about it.
Okay.
Right?
Yeah.
So completely rethinking how people think about diagnosis, which is, if you think about it, we're creating Dr. House and putting him everywhere and to detect any rare condition
Without the grumpiness.
without the grumpiness.
Yes.
Yeah.
So if anyone has questions, please, Billy we got some here. And I have a question. So let's imagine that we have some foundations who are going to watch this program. So I'm going to help you right now to talk to them, which is if you think in terms of timelines and milestones and deliverables, and you think of, well, we'd like $50 million, how does that translate into timeline, milestones, deliverables? And how will you know when you've achieved whatever it is you have in your mind right now?
Yeah, so the sizing for $50 million is over 4 years to deploy 32 sites,
Okay.
of which you could roughly think about it as 8 per year,
Okay.
right? That would provide all the infrastructure running at scale.
Yes.
Right. Now, obviously, we may be able to accelerate that, but now that the infrastructure's there, number one, let's go run these rare disease agents, which are ready to go. In fact, we're already independent of whether that funding is occurring, going to do this at 2 of the children's hospitals and just see how it behaves in the real world.
Yeah.
But we'll run a whole series of those agents during that period. We've already identified 20 different imaging applications where a researcher I'll give you a good example. There's a team at Boston Children's who's doing work in congenital heart disease detection, which happens to be the #1 killer of kids in Mexico, interestingly enough. The congenital heart disease detection has been trained only on data at Boston Children's. It works really well at Boston Children's. But the team there heavily recognizes that they've got to train it on far larger data sets. So that's a great example where we could go, hey, let's go train that congenital heart disease detection on EKG, frankly, and ultrasound on a 32x right training data set.
Including Mexico.
Including Mexico. Our intent has been international.
Okay.
In fact, yeah, we put a site in Italy and in London.
Wow.
Yeah. And Sao Paulo, Brazil.
Welcome trust.
Yeah.
Right. Look, here's a question from the audience, and it's sort of a personal one in a way. So here it goes. With the recent developments in AI, distributed learning, and valuable insights from current MDs from your podcast, what have you found challenging in scaling at the local and global scale, and what has been the highlight, most rewarding moment for you? Someone in this room has just asked this question.
I mean, I will tell you, it's always reward. Every conversation I have is rewarding. And why? I mean, I'll just give you an example. I today, as part of work we're doing with actually with Hyundai, I talked to a pediatric oncologist down at UCLA, and one of the things very interesting, people don't realize, I never had any, I mean, this is why it's fun. It's like I had no clue. Did you know that the survivorship level in pediatric oncology is right now 80% of the kids that have pediatric cancer can be cured?
Wow.
Is that like amazing?
I didn't know
Like it's
that.
way beyond adult medicine,
Really?
right? Yeah.
Okay.
In fact, in certain cancers, apparently, like leukemia, it's really high, like 95, whatever, right? So they're hitting the second part of the problem, which is they call it survivorship. So the challenge is, and there's a condition that happens called cardiac myopathy, if I pronounce it correctly, where the kid has been given chemotherapy to cure the cancer, but there's a side effect, which is it damages their heart.
I see.
So there's all these side effects that they know happen with these kids as they grow into adulthood that they need to both track, predict on, et cetera. So you start, back to my patient digital twin, you now start thinking about, well, I could have a patient digital twin who started at 4 years old at Rady's Children's and then keeps going and now is at some adult hospital where the doctor at the other end doesn't know that much about the kid, but I just told you I can ask all these questions of the patient agent. So when you say rewarding, it's like you could look at that, you go, we could help you with that. It's like really cool.
So you said in Rwanda, I think there's like one pediatrician.
There is.
So can you make it
Pediatric cardiologist.
pediatric cardiologist? Can you make it real for this audience? How would medical doctors in Rwanda use your distributed AI system in the real world to deal with children? Practically.
Yeah, I think, well, first of all, you're asking an application question.
I am.
And, you know,
You're not smiling right now.
yeah, our team is very much like the Apple team. We're an infrastructure. We're trying to build all this.
Oh, I see.
We actually don't know how to build Instagram. Just to mix analogies here.
It's a good point.
Right? Now, however, what I think is going to end up happening is first order magnitude, building these applications. I've been calling them red, green, yellow applications.
Okay.
So, you know, let's use my examples of, you know, brain tumors. Okay. You know, red, this is really a brain tumor, right? Okay, alert. And it could be not, you know, not a practicing physician who's there, just alert that this is true off this image. Oh, by the way, you should call or I will text or whatever, right? People who could handle this right away. That's red, right?
Got it.
Green is in, who cares? Yellow could be, you know, somebody else ought to take a look at this, right?
Okay.
And so you start to be able to, you know, take, let's call it this vast expertise in focal cortical dysplasia or FSGS and push it all around the world so that now you're just dealing with the last piece of it, right?
So earlier you said, well, look, when the Apple phone was created, they didn't imagine all the applications that could, and you're in the same position. So you're building the infrastructure like the Apple phone, and who knows what healthcare applications will be created using your infrastructure. Is that clear?
Absolutely.
Okay.
Absolutely.
I was paying attention, I guess. So the next question, the person who wrote it will reveal themselves to you because there's a note here at the bottom that says, I founded an AI imaging company because of Tim. So whoever that person is, there he is right there. He kind of asked a question. There's some words with a question mark. So it says FDA/NICE approvals. I assume you mean, does he need that?
Well, you will need it for any new trained AI model to be used in a hospital. You need to go through approval process,
Right.
which is assume that's on that big list of.
Right.
Yeah, and I think just to talk about that, absolutely that's going to happen or have to happen, et cetera. Although my observation is I don't know that because there's a lot of stuff that's quote FDA approved that I'm like, it's not like, what did it get tested on?
Right.
So I would argue they need to take the level up of what it
Yeah.
means to test this stuff.
If they even have a job after the cutback.
Well, I think they will. I think how this stuff gets regulated is actually an important issue.
It is.
I think what we're doing towards that is we're not trying to solve the application problem of focal cortical dysplasia, but what we're doing is by solving the problem at the infrastructure level, I can reduce the amount of effort it takes for an application to go do something.
Okay.
Right?
Yeah.
Today, that's a huge issue in medicine. Everybody builds vertical stacks. In fact, we've talked to companies that do sepsis prediction.
Okay.
Off of bedside monitor data.
Right.
And you talk to them, you go, oh, first of all, they got to go find a way to put a server in there. Second of all, how do they interface to the bedside monitor? Oh, how do they get a VPN out of there? And then, oh, now they get to do something with the data. You're sitting there going, they're wasting all of this effort and time on a bunch of infrastructure plumbing as opposed to actually working on the application. And part of the structures we built all create a governance framework for all of this. I mean, we get all the detail around that, but we're trying to standardize a framework that enables applications to move much more rapidly, whether it's FDA approval or EDA approval, et cetera.
So I know a lot of people who are interested in supporting and investing in cancer AI applications. So what you're describing, presumably, you were talking about tumors, you were talking about childhood cancers, 85% curable, something I think I heard. So is this something, your infrastructure, something that would be of interest to people who want to invest in cancer AI?
Oh, yeah. Absolutely.
Well, then we
100%.
have to talk afterwards, don't we?
Absolutely.
Yeah, this is really interesting. I have to say on behalf of this audience, I had no idea that it was potentially this big. And I mean, I looked at your website. It's really good. But this is a really big deal. That's a really big deal. And I think you're going to become like the Henry Ford. I mean, I think, Henry Ford basically, they were hand making cars for small numbers of rich people, and then suddenly they figured out, and he said, well, you can have any color you want as long as it's black. Ha, ha, ha. The reason is that black paint dries faster than any other color, and so for efficiency, it had to be black, right? So it sounds to me like you've got kind of a Ford-like, Henry Ford-like idea of scalability and applicability to a broad range of healthcare issues from children on up to dementia and Alzheimer's. I think this is a wonderful story. I have to say, I've done a lot of these programs, but I can't remember an example that was as potentially revolutionary as yours.
Well,
I'm on record as now saying that.
I'll quote you on that.
You go right ahead and quote me on that. So someone wrote, I'm not sure I entirely understand it, but this is a huge venture impact opportunity, ? And then says, should WGS, I have no idea what that means. What's WGS? Sorry?
Whole genome sequencing.
Absolutely. Whole genome sequencing. You again, you've got some good questions. Very good.
I invited him too. So, it's my fault.
Is he a plant?
Yeah.
Okay. Should he was on the payroll at one
Yeah,
point.
he was.
Should WGS be standard for children globally? And I think in Israel and a few other countries, I think it's standard. Is that true? Some places. So that's the question. Should it be standard for children globally, would you say?
Well, I'd say yes. I mean, that's an easy way to say yes. I know Radies has been doing a lot of work in this area to try to make sure that every kid does. And at some point in time, given the level of understanding people are developing around the genetic aspects of this, we actually spend time. There's a guy who's we should use the word ultra rare because there's all this funny terminology over in the FDA world. They call these orphan therapeutics, which are 200,000 people or less are affected by them, which some people will use that as the rare disease marker. Okay. This guy works on diseases that are like 2,000 people and less, right?
Is that right?
Yeah, and what's curious that he told me, he said he obviously is working in children's medicine. He got called into the ICU in the adult hospital that was connected to the children's hospital with 3 patients, which they had been trying to diagnose for months, trying to figure out what was going on. They ended up gene sequencing them. They ended up discovering that 2 of them had this ultra rare genetic disease, which obviously they had from childhood, only discovered, way late in their lives.
Right.
So there's no reason. I think one of the things we're all going to have to figure out is gene sequences are big data. How do you manipulate this? What do you do with it? How do you store? I mean, there's 100 questions, but there's no reason we shouldn't be doing that.
So when you said that this is a distributed system versus a huge facility in Austin, Texas, I think you said. So let's say in the hospitals in Helsinki and the hospitals in Cape Town, what have you. So how do these countries is there enough support for the 500 distributed children's hospitals data systems to make it work? Or is there incredible inequality in terms of what's available?
Well, I think the 500 children's hospital is no big deal. I'll tell you, Gertrude's Children's in Kenya, the facility is pretty world class. So
Okay.
I don't think that was never in our mind very difficult to think about.
Okay.
And what we're thinking about is let's go to another level, right? It's in the bush, right? Or in very rural parts of America, right?
How do you deal with that up in Willits?
Well, yeah. So if the way we've architected this, as long as there's electricity
Okay.
and an internet connection, we're good. So any site that you can see the sky and has a plug,
Okay.
this will work.
Wow.
Yeah.
Well, you've obviously got a dedicated audience in this room tonight for all sorts of reasons, and you've got a moderator who's completely and utterly in love with what you've said, and we're being watched potentially by investors and foundations. So I would say we're down, to the last, I suppose, 7 minutes or so, even though the timer says 2 minutes now. It suddenly switched on. Is that working now?
More or less.
More or less. Okay. So that's a bit of a shock. We went from 1 hour and 4 minutes to 2 minutes.
We're in football season. It should
Exactly.
be ultra accurate, right?
We have 2.5 minutes. So I'd like you to really basically make, a clear statement to those foundations on your list about why they should step up to the plate tomorrow morning and have a call with you to move this ahead.
Yeah, I think when I look at a lot of foundations or work that's been going on in the past in healthcare, and particularly pediatric healthcare, it's very isolated, right? They fund one smart team at Emory University. They fund another smart team sitting in Finland or whatever. And there's no leverage to it.
Yeah.
Right? Great we have 3 smart people there, but it can't go anywhere. It doesn't translate anywhere, right? And I think what we are saying, what we're saying to them is, if your mission is to improve children's health care on a global basis, which many of them do, that we have, there's all sorts of interesting examples of this, then this is a highly leveraged way to go do that, where we activate, right, smart people who are going to build the next focal cortical dysplasia application or congenital heart application, where they build that. I often, because of obviously how I've been connected, I talk to would-be pre-med students who are part of internship programs. And I often, because I'm being invited obviously by the medical staff, and I look at them, I go, "Are you sure you want to be an MD?" And I said, "Look, you go be an MD, what, you affect 10,000 people in your life? 50? I don't know, something like that. Go build software like we're talking about, affect millions of people." Mm-hmm. And I think that's really the key of what we're trying to do, is really to say to those foundations who obviously are interested in improving, reducing healthcare inequity, lowering cost, improving outcomes for children, here is a highly leveraged way to do that. And by the way, it's not just 10 smart kids in Silicon Valley saying this, right? This is a global effort, a global movement of leading pediatricians, experts in this, who are saying, let's go do this. All standing in our way is capital. That's it.
Which is not the hardest thing in the world to get, actually. Good ideas are harder. Yeah, well, I'll help you. I know a lot of people, and I'm on record of having said that. I think that this is, we're at the end of the time. This has been, for me, a profound program. I wish that the room was 50 times larger than this one. And I will do everything on behalf of the Commonwealth Club and my own work to draw attention to what you've done. Thank you so much.
you.
This has been fabulous.
Thank you.
Round of applause.